Now we are going to start about the case fatality rate, in which we are giving the percentages of death that occur due to any disease, any lethal disease. Like if 4 patients die among 10 cases of meningitis, then the case fatality rate is 40%, because case fatality rate percentage is equal to deaths divided by the cases. That will multiply by 100. For example, if we are having the cases, we are having 10 cases of meningitis or any disease in which 4 patients are going to die, then the percentage of CFR is 40%. Second, mortality rate. Mortality rate is the number of deaths in general or due to specific cause within a population over a defined period. For example, if 80 people in a town of 10,000 die over 2 years, the mortality rate is 4 per 1,000 per year. Okay? And this is a death per 1,000 people per year. It is a rate of death of the per patient person in a population. If you talk about the attack rate is a proportion of exposed people who become ill. And if 80 people in a town are exposed and 60 people become ill, then attack rate is 75%. For example, in same populated area, 100 people are living. In them, 80 people become sick and get the allergy and get the cough. Okay? And 20 did not got, then the attack rate will be 80%, like that.
Next up, demographic transition. Demographic transition model tries to answer the question why these patterns of growth and decline occur over the course of history. There are many factors that influence population growth and decline. Sate, these explain the country's level of development from agrarian to industrial once time. Okay, now before we get into the details of the DTM, it might help to break this whole mess down into individual parts. These 5 boxes represent historical stages starting with agrarian or farming societies here and then moving to developed industrial societies here. Now this line right here shows us the total population as a country moves through these stages, and over time the population is growing until stage 5 where it starts declining again. Okay, so all we're seeing here is that as a country goes through these 5 stages of development, population increases until that very last stage. Now the question is, why does the population do that in response to these stages? Well, let's add another layer, this time the birth rate, which looks like the opposite of the population curve. And that doesn't make any sense, right? Like if lots of babies are being born, then why is the total population so low over here? And if relatively few babies are being born here, then why is the population so high? A fine question, and I shall answer presently by introducing the last element of this model, namely death rates. And with that, we can go through the various stages. Stage 1 is known as the high stationary stage, and a society in this phase is pre-industrial and organizes its life around farming. So yes, the birth rate is high, but so is the death rate. So they basically cancel each other out. Lots of people born, but also lots of people living short lives and dying. So the population remains stable or shows slight increases or decreases. And as we stand today, no present country exists in stage 1. But then we move to stage 2, which is known as the early expanding stage, which corresponds to the beginnings of industrialization. For example, England in the mid-18th century was here as they transitioned from agrarian production to building factories all over the dang place and selling their goods on the world market. And here the birth rate remains high, but the death rate drops like a rock because with industrialization comes new medical technology, access to better food and vaccinations, etc. So because all of that is now available, it means people are living longer lives, but since they haven't slowed down on having lots of babies, what we see here is a population explosion. And it probably won't surprise to you if you've been with me these last couple of videos, but today, many countries in sub-Saharan Africa are in this stage. And then we get to stage 3, known as the late expanding stage, which is characterized by continuing industrialization and growing economic prosperity. Here the birth rates begin to decline fast, but still there are more births than deaths, and so the population grows slowly. And today, many developing nations are in this stage, but moving along to stage 4, and we are in the low stationary stage.
And here, a country is completely industrialized. Birth rates and death rates are pretty close to each other, which leads to slow growth or stabilization in the population. And because people are living so much longer in this phase, they've got new worries about aging populations like diseases of old age and care for the elderly. And today, most developed nations are in this stage. And finally, we get to stage 5, which wasn't part of the original model but has been added more recently to reflect declining populations, which is why it's called the natural decrease stage. Here, the death rate exceeds the birth rate, and so the rate of natural increase begins to decline. And an example of a country in this phase is Japan. Don't worry, guys, you're doing great. Just, believe in yourselves. Okay, so that's one explanation for how populations transition through history by considering birth and death rates as related to a country's level of industrialization. But before we move on, let me make note of two things you need to remember. First, this model only considers demographic transition through the lens of birth and death rates, but that's not the whole picture in the real world. In the real world, populations often grow or decline through migration as well. And then, second, this model was developed in the early 20th century to explain population trends in Western countries, and that means its explanations might not apply to how countries develop in the modern world elsewhere. And as you will move towards peak, it will present old's population. In first graph, the base is broader and wide. It mean it having high nuraku of babies, mean high birth rate. It having population marrow peak, mean these purge of older people is less. It mean death rate is high, life expectancy is short because of you guys focused on pyramid form base to peel. It's getting narrower because of low life expectancy and high death rate. But this broader and chord base mean it decade that population is growing. You focused on second one. The pattern of pyramid is constant, that indicate birth rate decrease with decrease in mortality rate. And in this, life expectancy is long due to wide peak. A stable population in third pyramid due to Noswell base indicate very low birth rate, and brighter peak indicate low death rate. This life expectancy is long well population is in declining phase due to low birth rate. When evaluating a diagnostic test, it makes sense to want to know whether or not the result of the test will change the probability that the patient actually has that particular condition. If, for instance, a positive or negative test result really doesn't change the probability that a patient has a disease, it's probably a test not worth getting. So, knowing all this, it brings us to our likelihood ratio. Now, the likelihood ratio for a positive test result takes the number of people with the disease who have a positive test result. This is also known as the sensitivity, and it divides this by the number of people without disease who get a positive test result, or 1 minus the specificity. Another way to look at this is it's equal to the true positive rate divided by the false positive rate. Now, the likelihood ratio for a negative test result is the number of people without disease who receive a negative test result, of 1 minus the sensitivity, divided by the number of people who don't have the disease and got a negative test result, or the specificity. This again is also equal to the false negative rate divided by the true negative rate. Now, if the likelihood ratio is greater than 1, this increases the likelihood that the disease in question is present, while if the likelihood ratio is less than 1, this decreases the likelihood that the disease in question is present. And this can be divided out into a table as follows. Here you can see that with a likelihood ratio of 1, there's no change in disease probability, but as the number increases or decreases from 1, you can see that the probability of disease changes. And if you look at the extremes of the spectrum, if you have a likelihood ratio of 10, this gives you a 45% chance increase in the probability of disease. While if you have a likelihood ratio of 0.1, this decreases your chance of disease by 45%. So with all that, what do you need to know for test day? Here is an example of what I mean. So you think you have a patient that has lung cancer, and you're told that you have a new test that has a positive likelihood ratio of 10, for the diagnosis of lung cancer if it is positive. You have your patient tested and the test is sadly positive. And here the question tells you that the patient had a pre-test probability of lung cancer of 5%. And they ask, what is the new probability of lung cancer? There you go, you've got it. It's 50%. Here, as we just stated, we had a pre-test probability of 5% and you had a positive likelihood ratio of 10 if you had a positive test. Again, this patient had a positive test result. So this results in a 45% increase in his probability of disease. Now, most physicians actually don't use this on a day-to-day basis, but it is important to know for your test as well as a part of the evidence-based approach to medicine. Graphic representation of event probability, it's here, versus length of time, it's here, that can be days, months, and years. It is useful for displaying time to event data and give rough estimations with stepwise changes. It used to compare survival probability or time to event between two groups, like in this graph. It is between people who are taking drugs after disease and one who is not taking that control group. And we are checking survival probability. It often used in cancer research to guide therapy, intervention, offer prognosis. Outcomes examined may include any event but frequently include mortality. So survival probability, that is survival of event at any time period, is equal to 1 minus event probability. In this graph, patients who are taking drugs for their respective disease having more probability for survival in X and Y time.
All right. Now let's look at some diagnostic tests. These include sensitivity, specificity, positive predictive value, and negative predictive value. You will be expected to calculate and manipulate these numbers for step 1, 2, and 3. So mastering them is important. First, let's review how to approach these questions dealing with diagnostic tests. You should always start by drawing a 2 by 2 table comparing the test results with the actual presence of disease, as you can see here. So, to review our table, a true positive is when the test is positive and the subject has the disease of interest. A false positive is when the test is positive but the subject does not have the disease. A false negative is when the test is negative but the subject actually has the disease. And a true negative is when the test is negative and the subject does not have the disease. So what's the benefit of constructing this table? Well, you can use this table to calculate the sensitivity, the specificity, the positive predictive value, and the negative predictive value. The sensitivity and specificity here are parameters that describe the diagnostic test itself, while the positive and negative predictive value describe how to interpret the test results in a clinical scenario. All right. So first up here, we have sensitivity. And it's the ability of a test to detect disease when it is present. The sensitivity of a diagnostic test is defined as the proportion of all people with the disease who test positive or the true positives divided by the sum of the true positives and false negatives. An easy way to remember this is in our 2 by 2 constructed table. It includes the values in our first column, as you can see here. After this, all you need to know is that the trues go on top, and you've created the formula for sensitivity. So when is a highly sensitive test most useful? Well, a test with high sensitivity is great at ruling out disease. This leads us to the mnemonic SNOUT. The SN stands for sensitivity here, and OUT stands for rule out disease. Here, if the sensitivity approaches 1, this is desirable for ruling out disease because it indicates a low false negative rate. And if you have a sensitivity of 1, the above equation shows that the false negative rate must equal 0. In this scenario, all negatives would be true negatives. Now, diagnostic tests with high sensitivity are often used to screen for disease. An example of a test with high sensitivity is an ELISA, which is good for ruling out diseases like HIV.
Now, specificity is the ability of a test to indicate no disease when the disease is not present. And specificity is defined as the proportion of all people without disease who test negative, or the true negatives, divided by the sum of the true negatives and false positives. An easy way to remember this is in our 2 by 2 table. These include the values in the second column, as you can see here. And again, after this, all you need to know is that the truths go on top. So what would a test with high specificity be good at? There you go, ruling in disease. This is often remembered with the mnemonic SPIN. Here the SP stands for specificity and IN stands for rule in. So here a specificity approaching 1 is desirable at ruling in disease, as this indicates a low false positive rate. And if the specificity of a test is 1, the above equation shows the false positives must equal 0, and therefore all positive tests would be true positives. Now, a diagnostic test with a high specificity is often used as a confirmatory test after a positive screening test. An example of this would be after a positive screening test for HIV with the ELISA, it is often confirmed with a highly specific test, the Western blot. Now this graph shows how you can shift the trade-off between sensitivity and specificity by adjusting the threshold of a positive test. This curve here represents patients without disease, and for our example, it will be no prostate cancer. And this curve here represents patients with disease, and for our example, it will be patients with prostate cancer. So here, we're going to use the PSA to illustrate potential cases of prostate cancer. And just an aside, these are theoretical numbers here to help us show how the table works, not to actually demonstrate the accuracy of the test itself. All right. First off, we're going to label the bottom of our curve. So after doing that, what do we see? Well, at 0, there is no one with prostate cancer, and all of the patients with prostate cancer have a value greater than 0. So using this lower limit for the test, this means that if you were to perform a prostate biopsy for everyone with a PSA greater than 0, you should theoretically miss no cases of prostate cancer. But with this, you're going to be doing a ton of unnecessary prostate biopsies. This means that in this case, your test is very sensitive. Now, for our example, let's change our PSA value to 4. Here, you can see that some patients with prostate cancer actually have a PSA less than 4. These are actually the false negatives. And if you only did a prostate biopsy with a PSA greater than 4, you would miss these patients, or their test would be falsely negative. With this, you can also see that there are a proportion of patients without prostate cancer who have a PSA greater than 4. Now, these would be our false positives, or our test is falsely positive, and the prostate biopsy would show them not to have prostate cancer. Now, let's move our PSA to 8. What do we see? Well, if you biopsy patients only with a PSA equal to or greater than 8, everyone would have disease. This would be a very specific test. But you can see that you actually miss a lot of patients who have disease but have a PSA less than 8. Another way boards like to test this concept is by showing you an operator curve like this one.
Here, the y-axis will be sensitivity and the x-axis will be 1 minus specificity. So with that in mind, which curve on the graph represents the most sensitive and specific diagnostic test? There you go, choice A. This test shows a sensitivity that quickly rises when specificity is close to 1. This would be a very good test in distinguishing between disease and non-disease states. Now, this curve, curve C, has no predictive value. That is, it can't tell disease from no disease. And choice D and E here would be distractions. Now, we still have a little bit more information to cover on our 2 by 2 table. First up, we have the positive predictive value and is defined as the proportion of positive test results that are true positives or the true positives divided by the true positives plus the false positives. Another way to look at the positive predictive value is that it's the probability that a person actually has a disease given a positive test result. An easy way to remember this is that in our 2 by 2 constructed table, it includes the values in our top row. And once again, all you need to know here is that the trues go on top. Another important point to note is that it's the positive predictive value that often shows up clinically, and this is when a patient asks what are the chances of them having a disease after receiving a positive test result. And here the patient is asking what is the positive predictive value for the said test. On the other side of this coin, you have the negative predictive value. And now the negative predictive value is defined as the proportion of negative test results that are true negatives or the true negatives divided by the sum of all false negatives and true negatives. Another way to look at this is the negative predictive value is telling us the probability of a person actually being disease free given a negative test result. And again, another easy way to remember this is looking at our 2 by 2 table. It includes the values in our bottom row as you can see here. And what do you think goes on top? There you go, the trues go on top, and again the negative predictive value also shows up clinically when patients ask what are the chances that they don't have a disease given a negative test result. Now, a critical point to remember is that both the positive and negative predictive value of a diagnostic test vary with the prevalence of disease. Now, what about sensitivity and specificity? Do these vary with disease prevalence? Nope, they sure don't. So with that, the higher the prevalence of disease, the higher the positive predictive value and the lower the negative predictive value. And to the opposite of that, the lower the prevalence of disease, the lower the positive predictive value will be and the higher the negative predictive value will be. And if you're having difficulty with this concept, remember the prevalence is defined as the number with disease divided by the size of the population. Or if you're using our 2 by 2 table, you take all of those with disease, which is our true positives and false negatives, and you divide this by the population, which is our true positives plus our false negatives plus our false positives plus our true negatives. If you want to test this further, you can put some example numbers in our 2 by 2 table to see how it changes the disease prevalence as well as affects the positive predictive value and the negative predictive value. All right. I know that was a lot of information to digest. So let's do one question for fun. It's discovered that the zombie apocalypse currently invading the world is being spread by a virus. This virus can happily be detected by an ELISA assay developed by the World Health Organization. Currently, there is no vaccine. The outbreak has started in China and thus the virus has affected 10 times as many people from China as from the United States. So with that information, how are the sensitivity, the specificity, the positive predictive value and the negative predictive value affected? All right. So thinking on it together, the sensitivity and specificity are not changed by disease prevalence because they are inherent to the test itself. However, if you're in China, the positive predictive value is increased. And what do you think about the negative predictive value? There you go, because the prevalence is increased, the negative predictive value would be decreased. And if you think of it this way, if you live in China where more people are turning into zombies, you are 10 times more likely to be a zombie. So even if the test is false, there's a greater chance that the test is a false negative because you are 10 times more likely to be a zombie. All right. Well, that wraps this up. See you in the next session.